Okay, so last time we talked about complex numbers as being single numbers that have two different parts, a real part and an imaginary part. And so generally they're written like this, where a is the real part and b is the imaginary part, because it's some real multiple of I. So b is always going to be a real number, but we're scaling I. And you can plot complex numbers on the complex plane, where the x-axis is called the real axis and the y-axis is called the imaginary axis. These are often abbreviated R, E, and IM. And every single number lives somewhere on this plane. So the numbers that you've used up until now all live on the real number line, which is just the x-axis, because they don't have any imaginary component. What about the number 2 minus I? Well, it's got 2 as the real part, but then you go down on the imaginary axis because of the negative I. And so here would be point A. Point B, hopefully you recognize these as coordinates on a unit circle. So I'm going to go over by 1/2, which is about here, and then I'm going to go up by root 3 over 2. And you don't know where root 3 over 2 is, but I've helpfully put a unit circle here, and you know that these are 2 points on the unit circle, so this has to end up on that circle. So that would be point B. Point C is negative root 2, which is about here-ish, and then root 2I would go up the imaginary axis by that same distance. So the drawing here is not super good, but it should be at a 45-degree angle in that direction, because the real component and the imaginary component are the same magnitude. Okay, so these are all rectangular form. And they're rectangular form because they're about horizontal and vertical distances. They're about a real component and an imaginary component. Complex numbers can also be written in a polar form, where you describe their angle relative to this kind of right-facing part of the complex plane, and the distance that you would take to get to them. I'm going to use this symbol to denote the angle to a complex value a, and this symbol to denote the distance or the magnitude of the complex number. So let's figure out the magnitude of all of these. So the magnitude of a. So here's a. If I want to figure out the magnitude, I can just use the Pythagorean theorem, because I know that that length is 2, and that length, the distance is 1. It's in the imaginary direction, but the distance from the axis is still a real valued number of 1. So I would say it's square root of 2 squared plus 1 squared is root 5, is the magnitude to A. The magnitude to B, we don't actually need to calculate, because you recognize these two numbers as being on the unit circle, so we know the magnitude is just 1, because the distance from the origin is 1. For C, let's calculate it for C. So we'll have the square root of root 2 squared plus another root 2 squared. So that gives us a distance of 2. Very nice. Okay, let's figure out the angles. So the angle to A, it looks like here I'll need to use some kind of inverse trigonometry. So if I imagine this angle here, the tangent of that angle would be this distance over that distance, or 1 divided by 2. So you could say arctan of 1 over 2. But that's not quite right, because the angle is always relative to this horizontal. So if I'm going to wrap in the clockwise direction like that, that would actually be a negative angle. So I could put a negative sign there, and that would be a perfectly good answer. Or you could imagine wrapping all the way around this way. So I could imagine it as being 2 pi, which is all the way around, minus that arctan of 1/2. So this angle is going to be negative. This angle is going to be positive, because we started off with a large angle and we're subtracting a smaller angle. And it's going to give us the angle all the way around to that point. Those are some minor technicalities. The important bit is realizing that you can express a complex value as its angle and its magnitude. Okay, so filling in the rest of these. So this one you actually know again. So think about what angle will give you that point on the unit circle. And if you're thinking 60 degrees, you're right, but let's express it in radians, pi over 3. And then for C, similarly, just thinking about the geometry of the situation, we know it's a kind of 45-degree angle facing this direction. So you could think about it as pi minus pi over 4. Or you could think about it as 1, 2, 3 pi over 4s, which is what I will do. I think you learned this last year, how do you add and multiply complex numbers, but just a quick review. When you're adding them, you add the components separately. So A was 2 minus I, and then B was 1/2 plus root 3 over 2I. So you combine the real parts together to make a new real part, and then you combine the imaginary parts together to make a new imaginary part. So I have 2 plus 1/2 would be the real part, and then the imaginary part, I guess let's write it and then simplify it. So I have minus I, and then plus root 3 over 2I. But typically what you would do is you would factor out the I to have just the magnitude of that imaginary direction. So here I'll have 2.5 plus -1 plus root 3 over 2I. So this is the real part. This, including the I, would be the imaginary part, but this is the scale factor on the imaginary part telling us what is that distance along the imaginary axis. Okay, multiplying. So multiplying works the same way. Multiplying works for any binomial. We'll multiply each thing here by each thing here. So 2 times -1 is -2. 2 times 3i would be 6i. Negative I times -1 would be positive I. Negative I times 3i is -3i squared. And now comes a thing that happens every single time you multiply binomials that are complex numbers this way. I squared is just -1. So this becomes plus 3, because -1 times the negative here becomes a positive. And so now I can take these two real values and combine them together to get 1 as my real value. These two combine together to give me 6 i's plus another I is 7 i's. So that's what the multiplying has yielded. It's given me 1 plus 7i. And you usually, well, not usually, you pretty much always simplify it into that final form.